So I see Andrew Viterbi. Is Andrew Viterbi here?
Yes, thank you.
Oh, nice. Thank you for joining. So Alan, why don't we wait for another like a minute, and then so we don't have formal introductions for these things. So why don't you can just launch in, but I'd wait for another minute just to let there be more time for anyone else who wants to join.
In the meantime, I'll just say hello to everyone.
Anupam, hi.
Hi, Anupam.
Hi, Todd.
And Mengji is on. Hi, Mengji.
Was eating my lunch, so that's why I wasn't.
No. Enjoy your lunch. I've been grazing for about 2 years now in this chair.
So I guess I'll say just a few words. We started these CILQ. I see, Alan, on your first slide, you have CLIQ.
Correct.
Was that intentional?
Somebody asked me that. Somebody asked me while I was on the committee like this week, and somebody said, "Well, why is it silk and not click?" I couldn't answer the question.
Oh, we had actually. You must have missed. We had a conversation about that in our group, and someone thought click sounded too clicky. So,
the reason I put up silk instead of silk is it was it reminded me of sort of somebody had once said that laser stands for light amplification of stimulated emission radiation, but that there was an apocryphal thing. Well, it really is an oscillator. So it should be LOSER instead of LAS.
Oh, that's terrible.
So but they decided not to call it loser instead of laser. So that was apocryphal. But then, decades later, I actually saw Charlie Towns, the inventor of the laser. So I asked him. I said, "Is this true?" And he said, "Yes." that discussion actually happened. So
wow.
And he also said I missed that meeting. So I'm just kidding.
Oh, really? You weren't there at the original laser meeting?
No.
Okay.
I don't even think I may not have been even a sparkle in my parents' eye yet.
The laser was preceded by Mesa.
Yeah. Moser.
Well, I was just going to say, we started these internal seminars in 2019, and Alan had actually given one before, as well as Salman of Estamir had given one. And then coronavirus hit, and we stopped doing it, but we're starting to do it again. And so now we have this Zoom format. And but it's just a good way for faculty to understand what other faculty are doing. And so I'll just let Alan, you can start whenever you're ready, but I would start pretty soon. Maybe you can just start now.
Sounds good. Thank you. And this is a it's a broad seminar. It's not, I'm not going to go into too much great detail of the specifics. Which I did the last seminar when I was very much detailed. This is fairly much broader. And please, people should stop me, and I'd be happy to answer questions, as I go along. So I gave a plenary several months ago and I kind of redid things to look at sort of what are the innovations and applications that are emerging in optical communications. And I use the word abound because there's a photo I have on the first slide. That's Tingyi and Edith Lee. Tingyi passed away about 10 years ago, and Edith passed away just a few months ago. Tingyi was a giant. In fact, he was a giant who known for the modes of a resonator cavity of the resonator that goes into lasers. When I was giving a talk about 15 years ago, I asked Tingy for advice about what I should use as a title, and he gave me a suggestion, and then he called me back an hour later. He says, no, how about this word? And then he calls me back. He's at a gas station. He says, why don't you use the word abound? Innovations abound. So I always want to give credit where credit is due. Tingy was like Mark Twain. He cared very much about using the proper word. So I want to thank Professor Neely certainly for organizing and inviting to give the seminar, my wonderful students and colleagues, and very generous support from various agencies. I was this is a slide. I did not show this, of course, before the pandemic. This is I'm in the same chair that I've been in. I think I'm Velcroed to this chair by this point. And I think when this was taken, I was also giving myself my own haircuts at this time. So as you might be able to tell, but this is my wonderful students. I feel so blessed that during the pandemic, they were all just so incredibly productive. They were producing papers at the same clip, if not faster than before. Simulation papers when we were in lockdown, and then they went back to the lab and had just wonderful work. And I'll talk about some of that as well. But really, what a wonderful group. I love showing this. This goes back just a few years. In 2015, one of the people who went back to Saudi Arabia, one of my students, he's now the chair of the department in electrical engineering in one of the universities in Saudi Arabia. But a few years ago, 2015, UNESCO had the International Year of Light, and at the ceremonies, there was I was familiar with optics, Galileo and so on. It was sort of very European centric. And the Saudi Arabian delegate to UNESCO, he said, he had a whole issue that you really have to go back to the original optical scientist. And that was Ibn al-Haytham. And Ibn al-Haytham had published 7 books on optics. And I went over to the Saudi Arabian delegate and I said, shame on me. So somebody caught this photo. I said, shame on me. I've been working in this field for over 30 years and I've never heard the name Ibn al-Haytham. And so that was from 1,000 years ago. It's good to know where you come from. I also complimented him on my students who were from Saudi Arabia, who were incredibly well trained, very bright, lovely people, and actually now have gone back. Another fun thing is, just to think about optical communications and how things have dramatically changed. When you do a data search on your cell phone, there's an enormous amount of optical communications that goes on. And in terms of the industry, the volume of components can be dramatic. So something that 25 years ago, data centers barely existed. But now, data centers, as many of you know, data centers are placed in colder climates or near bodies of water because of all the heat that's generated. There's because of all of the switching and communications, there's a lot of power loss and power dissipation and heat generated. Well, if you're going to if you look into a data center, so in an average size Google data center now, you would find over 1 million lasers that are connecting up at high speed information between servers, within servers. So whether it's 5 meters or 200 meters, and now even between data centers, of course, you're looking at optical communications and then an enormous number of components now that are needed to enable this to happen. Okay, now I want to. This is also kind of fun. I mean, I think most people are familiar with the predictions are very hard. Predictions are often wrong. And what is it about applications that drive innovations? So who could have anticipated 40, 50 years ago that you would use cell phones, and there's Facebook and social media and all the rest. So I tend to think about in 1982, the lab that I was in graduate school in Columbia, 83, they had gotten the first IBM personal computers. And at the time, as many of you may remember, well, some of you may remember, the students probably don't, people were saying, well, what are you going to use a personal computer for? And people would say, well, you'll balance your checkbook and whatever. You could never have imagined, I couldn't have imagined social media, Facebook, and so on. But clearly, sort of the innovation, the applications will then drive what's then needed to keep things going. And by the way, for the record, I've never balanced my checkbook on a personal computer. Now, this is sort of interesting. People knew for a long time, if you wanted to send, because coaxial cable, electrical cable, when you modulate high-speed data on it, there's an enormous amount of power loss. So you want to send high-speed communications over optical fiber. So you have high bandwidth and low loss through optical fiber. So people recognized very early on that you would want to go long distances, communications, optical fiber. What wasn't understood, and who could have imagined, was that latency was going to be a big deal. So that, what is latency? Latency is just how long it takes to, it's the speed of light. Why would it matter if it's a few milliseconds more or less? Well, it turns out it is a big deal. So on the upper right, there was, what you see in the upper right is that even though it was clear you'd want to go from, say, North America to the UK using optical fiber for high-speed communications, but who could have imagined that high-speed stock trading would be a big deal? So, but every millisecond is real dollars. So that if you can shave off a certain number of milliseconds with high-speed stock trading, it matters a lot. And so they invested, they deployed a new link just to have a more direct link from North America to the UK. And they spent $300 million in order to shave off just 5 milliseconds. So it was $60 million per millisecond. So this is real dollars. They're investing in it because of that. So, what does that do to innovation? So on the left side, one of the things that matters in terms of the speed of light is if you're in regular fiber, the index of refraction of glass is about roughly 1.5. So you're slowing the light down, as opposed to air, which the index of refraction, which governs the propagation of light, of electromagnetic waves, is the index of refraction is just 1 for free space. So if you want to speed up your communication link, there are certain places where they're putting in these microwave radio links, as you can see here, because if you go through air, you're going to go faster than through glass. Another innovation that people are looking at is hollow core fiber. As you can see here, this is an optical fiber. It's hard to see it, but there are these holes. This is a photonic bandgap fiber where the light is guided by these photonic crystals around it, like a grating that's keeping on focusing the light back into the center. The center is a hollow air core. And so most of the mode, the optical energy, is propagating in free space and can get to the other side faster, and that would reduce the latency. So is this going to happen? Not clear, but it certainly is driving a lot of innovation in this area. So what I'll discuss for the next little while in the seminar is this slide tells the whole story. It's that optical fiber communications was recognized early on, and it was clear. Optical fiber communications, Charlie Cow in 1966 published a paper to outline, if you had low loss optical fiber, you could have at high speed, high capacity communication system. In 1970, folks at Corning made the low loss fiber. And by the mid 80s, you were deploying optical fiber communication systems. And in 1988, they turned on the undersea optical cable. It was at a whopping 280 megabits per second. But from the concepts to low loss optical fiber to deployment was fairly quick. There were other ideas that were also thought about 50 years ago or more that are only now starting to emerge in a big way. People had thought about them, but there were innovations that needed to happen in order to make this 50-year-old story a reality. One of them is on the upper left, is free space optical communications. And this has been thought about since the beginning, again, that you're dealing with optics, which is a carrier wave of 200 terahertz, so you have large bandwidth to play with. But there were various issues in order to make this a reality over microwave, millimeter wave communication. And that's emerging now. On the upper right, if you are in free space, you're not limited to conventional optical fiber where the low loss is in the near infrared, but you can look at optical communications covering from the visible mid-infrared terahertz, really looking at ultra broadband systems. And the question is you needed innovations in order for to have sources and modulators and detectors in all of these regions. On the bottom left, this is about optical signal processing, and people recognized again 50 years ago that you can do optical signal processing on data. In fact, as I'll show, if you just take a lens, an optical lens, it's a great Fourier transform, but you probably wouldn't put a lens inside your computer to do a Fourier transform. And that's because you're not going to go from electronics to optics back to electronics, which is not very efficient, just to do a Fourier transform. But if your data is in optics and you want to process that data, it may be very efficient to keep it in the optical domain, to be able to operate on many different dimensions of the optical wave. The optical wave is wonderful compared to electronics. You have the phase, the frequency, the wavelength, the polarization. You have all sorts of things you can play with. And keeping it without going O to E to O conversion can be quite efficient. On the bottom right is the last thing. Again, it's a 50-year-old idea, but it took a long time to come to today. And that is about photonic integrated circuits. Decades ago, if people were able to do electronic integrated circuits and then put them everywhere, put them in thermostats, in your watch, anywhere you wanted to. Well, the watch even before smartwatches, they still had these. They could still have integrated circuits, but somehow, just because of the materials that were used, because of advances in optical fabrication, that only recently have there been foundries so that anybody can design a photonic chip, have it fabricated, and then deploy it wherever it may bring value. And that's really only a fairly recent thing. So let me start by discussing free space optical communications. So on the left here, the bandwidth is pretty clear compared to radio. Let's say you're going between 1 and 100 gigahertz of a bandwidth. Compared to free space optics, you're going to go between, say, 50 and 500 terahertz. Obviously, you've got an enormous amount of bandwidth to play with. You can modulate your data. Shannon tells you pretty clearly, this is great. And then you also have great directionality, because directionality is important because first of all, the carrier wave, if you have a higher frequency, you have lower beam divergence. So there's less loss because you can focus it like a laser beam. So you can focus the power where you want. And also where you care about privacy and security, there's a much lower probability of intercept. So whether it be between, in a battlefield scenario or anywhere, there's lower probability of intercept of eavesdropping with an optical beam. The problem is you have challenges that need to be dealt with. On the bottom left, if it's not in outer space, you do have to worry about the environment, the atmosphere. So there's turbulence, there could be obstructions, light matter interaction. So scintillation, absorption, and scattering can occur. You also, because the light does need to be pointed, very accurately, there is more of a challenge in terms of aligning the beams. So misalignment is a problem. And also you may want to go, the mechanical gimbals, you may want to go to electro-optic steering, which may be more integratable, maybe faster, more accurate. And so there's a lot of fun things. Oh, by the way, I just, for everybody, I'm not very good at looking at the chat. So, so Mike, I don't know if you want to, if there's a question somebody's asking, you can read it, or anybody can interrupt me. I'm perfectly willing to be interrupted. Now this is a fun slide. On the left is a picture from 1966, an IEEE paper from '66. And the right is from something I published a few months ago in the Optics and Photonics News. But in 1966, again, the idea that people have been thinking about free space optical communications for a very long time. And this was a 4-mile link in sort of the blue region at 30 megabits per second. To me, this is just amazing. Now, the problem is people did not use it, partially because the needs weren't there, sort of the applications for it. Most of the applications, yes, it's nice to say optics has more bandwidth, but millimeter waves, microwaves, radio, for the bandwidths that were needed, you can make do with radio type communications. Now, however, there really is a need for more bandwidth, and that's driving. So when you have a need, right, that's what drives this to going to new modalities. So on the right here, you really are seeing now, whether it be between satellites, between ground stations and satellites, we were funded by the AIER, the Airbus Institute at USC. To look at free space optical communications. We were funded by by the Air Force. We were looking at by drones, communicating with drones with the optical communications. And my students flew a drone in the courtyard outside of across the street from EEB, where they communicated at 200 gigabits per second with a flying drone. What's very interesting is we're funded also now by Muri out of Clemson, looking at underwater communications, and we were funded also out of San Diego, the Naval Warfare Center there. But as you notice, by the way, whereas in the air these beams look red because typically they would be in the infrared, underwater here these are green because the blue-green light has low loss underwater. Now, what are you competing with to, let's say, to an airplane? Light is competing with radio, right? So millimeter waves, microwaves, and whatever. What are you competing with underwater? Well, it turns out that radio waves are absorbed underwater. You're competing not against radio, you're competing against acoustics. So people use sonar and so on. And to use acoustic waves, you're limited to kilobits per second. So there's an enormous amount of interest to try to do even over, let's say, tens of meters, or let's say 100 meters underwater using blue-green light. If you can do gigabits per second, that's an enormous increase compared to acoustic communications in the kilobit range. Very exciting. This idea of this being emerging now is happening. So on the upper left, I'm just going to show this.
So Alan, I have a question on the previous slide.
Yep.
So I'm just wondering, like for an airplane or a drone, how do you align the beam so that you're shooting it at the drone or airplane?
So you need to have a beacon. So the excellent question. I'm probably not going to discuss that because of time. But typically, you'll also have a beacon that goes along with your optical signal. It could even be the optical signal, but there needs to be, well, not needs to, but often there's a beam going in both directions. And so you'll have like sort of, you'll set up a handshake for a link. So they're between the two sides, and there'll be a feedback loop. So in fact, my students, they made their own feedback loop. They built it so that you were always pointed in the right direction. There would be an error signal if you were off center. They have these quad optical detectors, quad meaning four different positions. So you can, if depending upon where in your detector the light is, you can see if you're off center, and then you have a little error signal, so you go back. And maybe you may want to do it instead of using mechanical steering, you may want to do electro-optic steering, which is basically like a phase array. You have like an antenna array where you can just change the different phase delay between multiple elements, and you can steer the beam. But that's
So
an excellent question.
I can see how you could maybe use radio frequency for the beacon, but if you're using optical for the beacon, I mean, would you have to have some like really huge spread of the optical signal, or?
By the way, Mike, you're touching on a very interesting thing. What if you had the communication signal in optics and the beacon in radio?
Yeah, that's what I was
That
thinking.
actually is kind of interesting, because then there are certain things that would stop the optical beam, but the radio tends to be, there's less interaction with the atmosphere. There's less, you're less obstructed by obstructions, which is repetitive. But so that there are hybrid systems. I don't think I'm going to talk about them, but there are hybrid systems to make them more reliable, to make them more robust. Maybe you even have two channels. So you have, and Andy Molish and I have been collaborating on, that such an idea of, to have, divide up your data between different regimes, so that it could be more robust and less prone to outages. But to your point, you could. Most of the systems, though, I think we've done have been the beacon, and the ones I've seen have been the beacon and the communication channel were both optical, and that's so that you could use the same components. So it was just sort of more cost effective. But I don't see why your idea is in any way, I think that's a good thing. I think that could be a good thing. So there are advantages to what you said. So on the upper left here, there's the German Aerospace Center. They're deploying. There's Google has put up. Facebook has a whole effort in terms of these, sort of high, these balloons, or these, basically the internet in low Earth orbit, or in high in the stratosphere. SpaceX has optical links that they're starting to deploy. The European Space Agency, and when you go very long distances, to be able to go, this has been, demonstrated 622 megabits per second, Earth to the moon, but it's going even beyond that. So to go to Mars, many of us have seen, of course, the helicopter that was flying on Mars, right? That wasn't using an optical link, but if you wanted to have much more bandwidth, you likely will need to go to optics, and there's all sorts of NASA has all sorts of discussions. Now, you have to have innovations to do that. One of the things that people care about, that a major advance in optical communications from a few decades ago, was the erbium doped fiber amplifier, broadband, low noise figure optical amplifiers. But if you want to put them into space, on the bottom left, if they're with radiation in space, the gain goes down. And so there's been all sorts of wonderful advances to make these rad hard, right? To radiation harden these erbium doped fiber amplifiers, and lasers, all sorts of optical components need to be radiation hardened. The other thing is to make very high sensitive receivers. One of the things, it's not so much a quantum receiver, but phase sensitive phase-sensitive receivers that use phase-sensitive amplification, for that you can just have a few photons to measure a bit. And this doesn't necessarily need to be a quantum receiver, but one that's very high speed to do gigabits per second and really outstanding work. This is, I just love this because this was, I thought, a revolution in the field, where, you know, something that was thought to be so difficult, but the work that was led to a large extent by Jianhui Pan in China, who was working before in Anton Zeilinger's group in the University of Vienna, but, you know, doing quantum key distribution from space, to do over 1,000 kilometers, to be able to send quantum key distribution, entangled photons. And there was a series of papers in Nature and Science and just all sorts of things. And it was something that people, you know, it just leapfrogged what other people were doing. On the bottom left here are all sorts of components that were used in what they flew. This was put up into space. The problem is that these were, you know, to a large extent, these were discrete components. What you'd like to be able to do is to go to photonic integrated circuits. So that would, you know, enable higher performance, hopefully lower cost, more reliability, and so on. And on the bottom right, there's been, you know, just lovely work going on and to try to package photonic integrated circuits as transmitters, as detectors. And I show here some of the references if you wish to look into more detail. Now, you know, one of the problems with in free space optics is you'd like to go to coherent communications, right? Just like you know, so much of you know, high performance communications is using coherent detection. When you do coherent detection, Shannon tells you that's great, right? You can get closer. So the Euclidean distance between, if you're using both I and Q, right? You need generally speaking, you have a lower SNR requirements. Most of this, well, the vast majority of optical communications in free space is direct detection, and even that has issues. But to go to coherent detection is quite difficult, and as I explain here. So if you go through the atmosphere, your nice Gaussian beam, as I show on the top, there'll be some turbulence, there'll be some beam wandering, and with this beam wandering, you'll get some power scintillation. And even with direct detection, you have to worry about this beam wandering and the coupling into your aperture, but people can do it as you know. And let's say on the bottom left here, you can have a you can have some sort of adaptive optics, just like you have for telescopes. You can have adaptive optics to correct some of this, what's going on in the beam wandering and this distortion that goes on in the you know, through the atmosphere. But the other thing that happens in the top here in this distortion is that your beam, your fundamental Gaussian beam, as you see here, is no longer a Gaussian, a fundamental Gaussian. It actually becomes, it couples into higher order spatial modes. And when you think of a spatial mode, you can think of, you know, go back to your basic electromagnetic theory. If you have a modal basis set, a complete basis set, you can describe any beam as a sum of modes that it's made up of, very much like you can have any time signal is made up of a Fourier series of cosines, and all these cosines are orthogonal. So all these modes are orthogonal. If you look here in the middle, if you want to do coherent detection, so normally you have your Gaussian beam, your data channel here, and you would, you know, when you think about a local oscillator, like over here, you normally have a local oscillator to do coherent detection, beating with your a Gaussian local oscillator with your Gaussian data channel. Now, the problem is your data channel is now coupled into all these higher order modes. And in your detector here, which is your optical to electrical mixer, the only efficient mixing of power is between modes that are similar. So if your local oscillator is a Gaussian, it's only going to mix well with the Gaussian, the fundamental Gaussian left of your data channel. Power coupled to the other modes is not efficiently coupled, so that's a problem. One approach that was done, pioneered at Bell Labs, was to basically try to recover all of these modes and have sort of multiple local oscillators, or a local oscillator that's split. So you can basically go through free space, you couple to all these all these higher order modes, and then detect them in a multi-mode fiber, separate the modes, and then have a bunch of coherent detectors and then sum them up. It's certainly it's a very good approach. What I'm going to show you next is an approach that my wonderful students published in Nature Photonics a few months ago. And what it does, it relies on looking at the mode, all these modes that appear. So what I'm just showing here are a bunch of Laguerre Gaussian modes, where you have the amplitude on the top and the phase change on the bottom. And you can have a two-dimensional set of L and P modes. So every beam in the two-dimensional space, the spatial distribution in amplitude and phase, you can look at it as being in the L azimuthal direction. So in the azimuthal direction, in this case of 5, you would have 5 different 2 pi phase shifts around the center. So you actually have a phase change around the center of your beam. And then the P would be the number of rings in the radial direction, or how the phase may change in the radial direction as well. With that, this is how my students, led by Run Zhao, how they attack the problem. On the top here is what I described before. You have a Gaussian beam. It goes through turbulence, and then the modes are coupled to all these LP modes of the Laguerre Gaussian set. Now the problem here, you can detect this, of course, you can detect this if it's just direct detection, then you can just recover all the power. But if you want to go to coherent detection, which in general has better OSNR requirements, and you want to recover on the left here, say a 16 QAM signal, if you go through a turbulence, your Gaussian beam is spread, the power is spread to a lot of other modes. When you try to then mix it at the receiver with a local oscillator that is only a Gaussian beam, it doesn't couple well. The local Gaussian beam will only couple to the fundamental Gaussian of now your data signal. And then the IQ, it's very difficult to recover. So what my students did is they sent a pilot tone from their transmitter, as you see here, a pilot tone along with the data channel. Both of these are Gaussians at the transmitter. Both go through the turbulence. Both experience the same modal coupling through the turbulence, the same modal coupling matrix. And then when you go into your square law detector, what you get is the coupling matrix U, the coupling matrix U, but then because of the square law detection, you also get the conjugate of U, of the modal coupling. So you get U and U star, and you can automatically undo the turbulence effect of modal coupling. Every one of these pairs, whatever gets coupled to higher order modes, the power from the data also is in the pilot tone. And you basically get this very efficient automatic mixing, and you can recover almost all of the power gets coupled back into your, so to speak, your fundamental mode. And you can recover use this pilot tone, and it's self-coherent, and you can recover I and Q. Just to show you, this is results from this Nature Photonics paper. This is the I might as well show this here on the right. This is with stronger turbulence. This is experimental work. This is on the left here. This is the loss that would be the loss in the mixing between the data and your pilot tone, which is acting like a local oscillator. And then this is a traditional case of a local oscillator-based heterodyne detection. And you can see that the amount of potential loss is huge. Again, because of this, the modal coupling is happening from turbulence only to the data here and not to the local oscillator. This shows you the result, and I'll only show on the right here. This shows you with the approach of this pilot tone, you can recover 16 QAM on 2 polarization states on 2 orthogonal polarizations. So this would be 2 different data channels. And if you don't use the transmitted pilot along with it, and you're only using a local oscillator, as you can see with strong turbulence, you can't readily recover the I and the Q. Now, underwater, I'll just mention here that, again, there's some wonderful work underwater. You're competing, you can't do the normal optical fiber communications of the near infrared because there's too much loss underwater. You can't do RF because there's too much loss, but you can use blue-green. And the challenges, though, are how do you use blue-green? There should be innovations either in wavelength conversion, so you can do modulation and demodulation, modulating high speed and recovering the high speed using the near infrared, which there's an enormous industry. So there's all this optical fiber communications companies making products and that you can use, but you would have to wavelength convert, and typically that's done using nonlinear optics. When you mix in nonlinear optics, you mix 2 waves, you get the sum and the difference frequency. So you can wavelength convert down to the blue-green. Or you can innovate and make native devices in the blue-green to do high-speed communications. And there's work going on in both. Now, one of the fun things is you can do, people have shown, and we've shown in the lab, we've done tens of gigabits per second in the lab through water. A fun thing is we're also looking at, my students led by Hao Chen are looking at through the interface of the water, the air-water interface, where you have turbulence below the water, above the water, you have aerosols, you have the curvature of the water, all sorts of things that can disturb. It's all dynamic, harsh environments, but there's wonderful innovations going on. Because again, you may be above the water, you may have something submerged, say a few meters below the water, you may want to communicate at gigabits per second. I'm going to skip over the orbital angular momentum modes, just simply because I talked about that last time. So I'm skipping over all of this for the sake of time. Now, one of the fun things, this is now, we're not in fiber. Let's think about outside of fiber. Lynn Mollenauer, he one of the pioneers of soliton optical communications, made a comment that, if you really think about optics and as comparing it to radio, he made this comment. He said, you can transmit infinite bandwidth, which is what people in radio think about optics. You can transmit infinite bandwidth, but only over 0 distance. You really need to innovate to overcome the challenges. Now, on the right here, in optical fiber, you can have chromatic dispersion and polarization effects, nonlinear effects. Now, nonlinearity of the glass is really the key thing, keeping optical communications in fiber away from Shannon's limit. That's one of the key issues of trying to reach Shannon's limit in fiber. Now, in free space, you don't have nonlinearity per se, but you do have issues of beam divergence, the weather, such as turbulence, you have obstructions and all sorts of other things. What you do have in free space is the ability to operate over much wider wavelength ranges. So what I show here is, in red here, is the transmission window of the C-band of optical fiber, which when you look at the transmission bands available to you through the atmosphere, and certainly in outer space, you don't even have the atmosphere, but it's, you have a much broader bands. So there's really this, it's an opportunity. And as I mentioned before, either trying on the bottom left here to have native devices in each of these other bands, such as in mid-infrared and terahertz, or in the visible, or to use mature technologies that are in this telecom C-band, 1.55 microns, and wavelength converted. And on the bottom right, I'm just showing that there, and Mingji and Hossein, just two examples, very familiar with doing wavelength conversion using nonlinear optics in waveguides, but so photonic integrated circuits to shift light that is being modulated at high speed from 155 microns to all sorts of other regions. Now in free space, of course, you can go from the visible light on the left here all the way, well, radio, acoustics is not electromagnetics, but still, there's all sorts of fun things and trade-offs, right? At lower frequencies, you tend to have lower frequencies. There's less interaction with matter, but you have an enormous amount of divergence, and you also have less bandwidth. So there's all sorts of trade-offs for real systems. I show this simply because we worked on some terahertz. That's why a lot of interest in terahertz now, because sort of in, I would say, sub-terahertz, 100 gigahertz carrier waves to a terahertz. There's a lot of interest there for communications because there's more bandwidth available to you than in millimeter waves, but you have less interaction with matter than in optics. So you get sort of more bandwidth, but less turbulence effects. So that might be a sweet spot. And this is just shown here for terahertz innovations. Again, terahertz may have larger bandwidth than millimeter waves and less affected by turbulence than free space. On the right, on the upper right, is just showing you this absorption here, this low loss attenuation region in this sort of sub-terahertz region. And one of the things why optics, why optics is so valuable for this area for terahertz communications is because it's very hard to work with terahertz using electronics. It's also hard with optics, but optics gives you this wonderful way of generating a terahertz beam. So if you have two lasers on the bottom left, and lasers, right? So many of us on the call love lasers. I love lasers. They're very stable. And if you take two lasers that are at, sort of 200 terahertz, and you separate two lasers by a terahertz, you mix them in a photodiode, you can generate the difference frequency very well and very stably. And so you can generate a terahertz beam. And if you modulate it at high speed, that gets translated in the optical domain, it gets translated to terahertz. And there have been wonderful work. This is a 16 QAM signal here showing we've done it as well. Terahertz beams using a space division multiplexing in the terahertz region. What about mid-infrared? Well, there's also sort of great issues in the mid-infrared, whether they be, this is the absorption here. There's low absorption in sort of 3 to 5 micron light, 8 to 12 micron light. There's a lot of interest because there's less interaction with matter. So if you want to communicate or sense or do imaging through fog, through dust clouds, there's a lot of interest in the mid-infrared. And as I show on the upper right here, again, compared to the infrared, going to the mid-infrared, there's lower, generally speaking, you can get to lower loss. Now, in terms of native devices, that's one of the things. You could have quantum cascade lasers on the bottom left here. Some wonderful work that was published. You can modulate quantum cascade lasers and produce gigabits per second. You can do what we did, which was operate at 155 in the near infrared and use nonlinear optics to go to the mid-infrared, do your communication link, the medium there, and then go back to the near infrared and again, using nonlinear optics. On the bottom right, we did multi-wavelength communications. So wavelength multiplexing, this was published we published it just recently, different wavelength division multiplex channels in the mid-infrared. I'm going to skip over these two just in the interest of time and go to optical signal processing. So I mentioned the way at the beginning that, it was recognized 50 years ago that you could do signal processing using optics. So a lens does a Fourier transform. But what you want to be able to do with signal processing is, if it's already in the optical domain, you want to keep it in the optical domain to avoid an inefficient optical to electrical to optical conversion. That's really the key. You don't want to, you don't want to go into optics just to do the processing per se. But if it's in optics, you want to be able to process it natively there, and then to operate on the amplitude, the phase, the wavelength, the polarization, and be able to process at the line rate. So if you have a data stream, and John Habiff is leading an effort now, and wonderful collaboration. If you can take 100 gigabits per second or a terabit per second and process that, do something to it, do some correlation function, some bit pattern recognition, that would be great. And one of the things you could do is on the bottom here, which my students over the years have done some very nice work. If you have a large amount of data in the terabits, to do some pattern recognition, and optics can do a few things really well and really fast. And so maybe you can correlate over terabits, correlate very rapidly in optics, get it into the gigabit range, and then maybe you can do more advanced signal processing in the electronics, and then maybe some user can look at what's the output. One of the key things you can do, again, with nonlinear optics, is do things like wavelength conversion. It's a very simple thing, and that could be used to do multicasting of signals in like a networking environment. So again, I defer to Professor Neely for multicasting, but you can take a nonlinear element, an optical nonlinear element. You come in with a data stream on the red, you can come out on the blue. You can even come in, here on the black, and multicast them to many other channels. As long as this is all done coherently, this can be very efficient. On the bottom left, and many of you are familiar with these optical frequency combs. This is a ring resonator pioneered out of many places around the world. Specifically, we use one from Tobias Kippenberg's group, but this is a paper from a wonderful group of folks in Switzerland and Colombia and other places. So, but this is an optical frequency comb where you have numerous frequency lines. They're all coherent with each other, and if you mix them in a nonlinear system, you can take all of these comb lines and take a data signal, as you can see on the bottom right here, and multicast it in a networking environment to distribute your signal to do all sorts of fun networking functions. One can also do all sorts of optical signal processing. The concept of a tapped delay line can be done in optics. This is an optical tap delay line where you split the light here on the bottom left. You can have amplitude and phase weights applied and various delays applied, and then on the output side, and one can do all sorts of fun things. And you can do this, the light is flying through this thing. This can all be done on a chip. And again, Professor Hashemi's group is working on this as well, and you can do wonderful things. I'll skip over a couple of these and go straight to try to finish up in the next few short minutes on just to tell you issues about foundries to do photonic integrated circuits. So I had a student. So again, this has been around 50 years ago. In the early 70s, you had Stu Miller from Bell Labs with published papers on photonic integrated circuits. You had Amnon Yariv. There was early 70s. There was I think it was an IEEE conference in Iran. He talked about integrated optics. Amnon is a distinguished professor at Caltech. So this idea has been around, but with electronics, people did this decades ago to have foundries, TSMC, to basically put integrated electrical circuits anywhere. They're cheap, they're high performance, put them wherever they bring value. We want to do that with optics. And it took a long time because there are many different material systems, many different components, and there needed to be advances. So this slide is really to show 15 years ago, my student, one of my wonderful students, Lin Zhang, he's a professor now in China. He loved waveguides. He loved photonic integrated circuits, but we didn't make anything. And we couldn't get anybody else to make anything, and we couldn't pay somebody to do it. There were no foundries. So he came out with a bunch of wonderful papers to do, and he simulated this. These are waveguides. This is a ring resonator, and he made a filter and he made a modulator out of it. But he didn't actually make it. He just simulated it. And each of his papers, a year or two later, was fabricated by somebody that had a facility. And this was just some work that was published from Hong Kong, but somebody was always a year behind us to do this. And but now there are all these foundries around the world. And this just shows how my wonderful student Hao Song was leading this effort along to make these meta-surface structures fed by four different waveguides to produce an orbital angular momentum beam coming off of the surface. So he designed it, fabricated it, along with Hui Bin, another one of my wonderful students. They made a meta-surface, they made a ring resonator, they made Mach Zenders. They had they designed it with tools and then fabricated it. But this is a real wonderful thing. Academics can now make things. The small companies can design and make things, and things, hopefully, the idea that there are now over 30 PIC foundries around the world to really get things made, to bring optics to where it can bring value. And I think we're only seeing the beginning of that happening now. I will just say that when I graduated back in the late 80s, I told somebody asked me, one of the professors asked me, and he was very well known. He said, "What are you going to do?" I said, "Well, I'm going to go into optical communications." And he said, "Why are you going into that? It's a mature field that doesn't have much growth." And that's because at the time, the technologies, what this shows is the bit rate distance product versus year. So there was, a lot of work going on in single mode fibers and single frequency lasers, but the erbium dope fiber amplifier and wavelength multiplexed communications hadn't really taken off yet. So the technologies of the time were kind of, not producing as much growth at that point. But the party had just barely begun, and there's an enormous amount of innovation that went on in terms of spectrally efficient modulation of formats, space division multiplexing, and so on. So this has just been a party. In summary, I'll say that this is an enormous amount of, we're just, I think, scratching the surface in terms of the applications of where optics will play a role, whether it's under the ocean, of course, but also anywhere. I mean, will there be optics in a smartwatch in 10 years? Perhaps, right? And if it brings value, hopefully it will be there. And I'll just end by showing this, just to show my advisor, Professor Osgood. It took me 20 years after I graduated to realize that I knew who my grand advisor was. That was Professor Ali Javan from MIT, but I never knew that his advisor was Professor Towns, who was, again, the inventor of the Maser laser, or got the Nobel Prize for the Maser laser. So after that, I never called him Charlie Towns anymore. I always called him Professor Towns. But I encourage all the students who are listening, find out where you come from, and that's there's a lot to be said. And I get great joy of my students who've become professors in different generations. And when I go around the world, I could tell you, I was in China a few times. When somebody comes over to me, I remember much more when a student comes over and says, "I'm your grand student." I remember that. I may not even remember the talk that given later in the conference, but I'll remember that one of my grand students came over to say hello. So anyway, with that, I'll thank you very much. So I guess I'm welcome to any questions you may have.
So I have a question about one of your early slides. It was a picture of a data center. And
Yes.
so I noticed, so you mentioned that there could be some optical signals, even free space optical, going between those things. And so I can kind of imagine maybe within one of those structures. But I'm wondering what happens if someone walks down the little hallway that's in between these things? Are they going to get shot with lasers?
So excellent point. So you really have to be very, so the designs that I've seen, and by the way, there are people on this who are here may know a lot more than I do. And by the way, I will say that Todd gets the prize for the most number of posts in the chat. Thank you, Todd. And by the way, so the designs I've seen was where there would be these lasers that would be free space lasers put on top, not just top of rack for those who do networking, right? That's the top of the rack, but really on the top of the, physically on the top of the rack, where it would have to go or bounce off of mirrors on the ceiling. Because right, otherwise you're going to be stuck with obstructions, right? So you were thinking of it that the person could get zapped. I'm thinking of it from the data channel goes down, right? You want the data channel up. So yeah, you do have to worry a lot about obstructions. And obstructions are the big deal for optics because it is focused, because it interacts with everything. So that's one of the key. So in terms of rich areas to look into, I think you could certainly think of obstruction tolerant beams, yeah, but in terms of data centers, yeah, that's what I've seen. Yeah, it would be sort of above everything. Hopefully the sprinklers won't go off if anybody lights a cigarette. Photon torpedoes. Are phasers light, Todd? All a phaser isn't it an angle? Isn't it a direction and it's a vector, no?
I think that the way they use it in Star Trek and the way they use it in basic engineering are not exactly the same.
Alan, I wanted to say, I think you left out maybe the most important thing about free space optical communications. It's the most important modality of communication in my life. I think you have it, the TV clicker, right?
Bingo.
Yeah.
I remember the first time I didn't have to get up. I was like, I didn't have to get up and tune the dial. It was like magic.
Yeah. Where would we be without it?
I don't think there are any photons and photon torpedoes. They should call them boson torpedoes. If you really, I'm going to start a campaign. It really grinds my gears that.
I have another question, regarding the wireless communication, where you mentioned you can beat, you can beat a modulated signal with another optical signal, then generate terahertz for the wireless communication. I think I remember that. I mean, there's one slide. I was wondering its alternative way is just to convert it into the electrical and then mixing in the electrical domain. What are the pros and cons between these two approaches?
Excellent question. Actually, and I think there are people on here that probably know more than I do. It's a good question. I mean, one of the things you need is good linearity in your mixer, right? So, I mean, but there's challenges, of course. I don't know. There are these slides I've seen where you look at sort of to do something at a terahertz, electronics and optics sort of don't naturally do that. Either one of them doesn't naturally do it. So, I guess which is easier? Both, and frankly, over the last decade, both have made major advances. So electronics is moving up in frequency and optics is moving down in frequency. Which is going to become easier? I think that's a good question. And what are the challenges? I think for the so I'm more familiar with the optical challenges. And again, there are people out here. I tend to think that if you're going to do high data rates, there's a lot of value in the optical approach because you can modulate it at enormous speeds. So you're going to modulate the data in the optical domain. You do need good linearity and wide bandwidth in the detector. So the detector is an issue. You may want to look at, so Dan Middleman in Rice has done some wonderful work in sort of
He's at
terahertz
Brown
communication. Sorry?
He's at Brown now.
He's
Oh, he's a
brown.
Brown now. Okay. Thank you. I guess since he already, yeah, so it means somebody likes him.
Regarding to this, I have another question. Do you prefer a modulator with terahertz bandwidth or like 10 modulator with 100 gigahertz bandwidth?
I prefer the lottery, $1 a year for 1,000,000 years. No, so it is a, Todd, please put something in the chat. There's how you slice it. Every optical system. So Menji, that's a fantastic question. Every optical system is different because it's a trade-off, right? Sort of like, I'm guessing actually you're going to, whatever that's been asked for decades, as far as like, how much bandwidth do you want in one channel, and then how many parallel channels do you want? What's ended up happening is they've just pushed both on both. They just, every time it happens, they just keep on going to more bandwidth per channel. So the answer will probably end up being, if you look out a decade, they're going to want a terahertz on, as much on each channel, and then give me more channels. So they're just, which is a bad answer. Which is, yeah.
Yeah, thanks. I have another one. What do you see is the breakthrough moving to the PIC kind of circuit? I know you mentioned optical frequency comms, which, I mean, besides nonlinear frequency conversion, you mentioned are like frequency comms, which I think there's a lot of like power and SNR issues regarding to that as compared to using many VCSELs, for example, to do that. So did you see that as a breakthrough, or did you see something else? If something is done, and that will like benefit a lot in optical communication system in the field of PIC?
Yeah. As you're asking the question, for those of you who don't know, so Mengji is an expert in nonlinear materials, nonlinear devices, and some of the materials that may not be, there's silicon photonics, which everybody talks about, and then sort of lithium niobate type, high-speed lithium niobate and so on. That's a hard one. I do think that was one of the problems of over the last 50 years, is that different materials did different things well, right? So that you couldn't get like one chip that did everything well. You were gonna always sacrifice something. The things that had lower loss weren't the ones that had higher nonlinearity, that weren't the ones that you could drive at high speed. It wasn't an optical material, it wasn't at the right wavelength. You were always sacrificing something. So I mean, if you were looking at a breakthrough, I remember one of the early silicon photonics, it was a DARPA program. I won't say which one, but they had like, these numbers to hit, these metrics to hit in the BAA. And it was like, you had to hit a certain number. And then below it, it was like, except in silicon, you could do this, which was like an order of magnitude lower because they knew you couldn't do it. And so, it's sort of, that's really what you want. You want to be able to have this unified thing. Again, there are people on here who know more than I do. Wade, I don't know, what do you think?
No, I don't know enough about PIC. Yeah, I think Benji does more.
Yeah,
Yeah,
but it's the unified thing that's a big deal, I think.
Yeah, that's something I've been thinking for a long time, but like maybe we can discuss more like offline.
I would love it. I would love it. So yeah,
If
and
you
now
will be
that I'm
on
back,
OSP,
I'm
I
actually
will
back
be
on campus. I'm going to campus after this. I just wanted to be in this chair. I'm telling you, this thing is I'm never leaving this thing. I should take it to my office.
Yeah.
There you go. Anyway, so maybe, I don't know, Mike, is that,
Any other questions or comments?
I think just Todd and I should stay on so that we can just chat in the private chat.
All right. Well, for everyone else, I guess we'll wrap up. Thank you for coming, and thanks to Alan. I think we've already sort of given Zoom applause, so I'll give you 2 thumbs up. And thanks again.
Thank you.